This video is on the photoelectric effect. If you are interested in learning more about atomic, quantum, and nuclear physics, then please do read the book, The Quantum Story, A History in 40 Moments by Jim Baggett. I read the book, it's amazing. Hope you can too. Also watch and take notes on all the videos on this website. Question 1. Briefly describe the photoelectric effect. In the photoelectric effect, the electromagnetic waves strike metal and the electrons are ejected from the metal. Albert Einstein earned the Nobel Prize in Physics for discovering the photoelectric effect in 1907. So it's a pretty big thing. Question 2. About how long does it take for the electrons to leave the metal during the photoelectric effect? The electrons leave the metal instantaneously. Question 3. Define critical or threshold frequency. The critical frequency or threshold frequency is the minimum frequency needed for the photons to eject the electrons in the metal. Each metal has its own distinct critical or threshold frequency. So if there's a minimum energy needed, there's also a if there's a minimum frequency needed, we know E equals HF. So there's also a minimum energy needed to free the electrons in the metal. Question number 4. What will happen to the metal if the intensity of the electromagnetic wave is increased while it is still below the critical or threshold frequency? Will the photoelectric effect occur? The answer is no. The photoelectric effect will not occur if the intensity of an electromagnetic wave increases, which is still below the critical frequency or threshold frequency. This is important. When discussing the photoelectric effect, the term intensity means number of photons per second as well as power per unit area. Question number 5. What will happen to the electrons if the intensity of the electromagnetic wave is increased while it is above the critical or threshold frequency? The number of electrons leaving the metal will increase. The kinetic energy of the electrons will not change. Question number 6. What is the work function? The work function, psi, is the minimum energy of the incoming electromagnetic wave required to remove an electron from a metal. The work function has units of joules. The value of the work function depends on the metal. So different metals, different work functions. Question 7. Describe the equation E max equals HF minus psi. So we're going to see that equation every now and then in physics textbooks. So the energy coming in equals the energy coming out. What's the energy coming in? It's the energy of the incoming photon before it strikes the metal. What's the energy going out? It's the energy of the work function, meaning the energy required to free the electron from the metal, plus the kinetic energy of the electron that's freed. Okay? So what's the energy of the incoming photon before it strikes the metal? It's E equals HF. And what's the kinetic energy of the free electron? It's kinetic energy maximum. So rearranging, we get kinetic energy maximum equals HF minus psi. So this equation tells us the maximum kinetic energy of the electron ejected from the metal during the photoelectric effect. Question number 8. Draw a maximum energy versus incoming frequency graph for 3 metals. What does the horizontal and vertical intercepts tell us? What does the slope tell us? Okay. So the horizontal intercept is when energy max is 0 joules. This is the minimum incoming frequency required to free the electron. The free electron will have no kinetic energy when energy max is 0. We can call this the horizontal intercept the threshold frequency f sub 0. So now at the threshold frequency, total energy in equals total energy out. Energy of the incoming photon before it strikes the metal equals the work function, the energy needed to free the electron, plus the kinetic energy of the free electron. So the energy of the incoming photon before it strikes the metal is hf. Once again, the work function is psi. And when energy maximum is 0, we know that E max is 0. In this case, hf equals hf sub 0, and the h's cancel. Okay. So let's talk about the vertical intercept. The vertical intercept is when f equals 0 hertz. We could see that here. The vertical intercept is when f equals 0. Once again, total energy in equals total energy out. This is the law of conservation of energy. The incoming photon's energy before it strikes the metal is equal to the energy after, which is the work function energy. That's the energy required to free the electron, plus the kinetic energy of the free electron. So if f equals 0, which we substituted here, we get phi equals minus E max. And the slope of the line tells us Planck's constant. So E equals hf. So h is delta E over delta f, which is the slope. Delta E vertical divided by delta f horizontal. Question 9. Describe step by step what is happening in the lab setup below. Okay, so this looks kind of complicated. Looks like we have a battery on the bottom, and it's a variable battery. Okay, we could decrease or increase the voltage from that battery. It's connected to an ammeter in series and a voltmeter in parallel. And here we have a vacuum on the top. We have an anode and a cathode. Okay, so looks like parallel plates. It is parallel plates. So step 1, electromagnetic waves or photons strike a metal plate. Step 2, the electrons in the metal plate leave one plate to the other plate. So step 1 you could see in the image. A photon or an electromagnetic wave strikes a plate. Step 2, in green, the electron goes from one plate to another plate. Step 3, the potential difference across the variable battery is increased until the current in the ammeter reads 0. This is called the stopping potential or stopping voltage. So let's see what's happening. If the voltage from the battery on the bottom is 0, we're going to get a current. Okay? If we continue to increase the voltage of the battery, the electrons from the battery move to the right. So they're going in the opposite direction as the electrons from the photoelectric effect. Now, if we increase the current from the battery enough, or the potential difference enough, we're going to get an ammeter reading of 0. That's called the stopping voltage. Question 10. Define stopping potential or stopping voltage. The stopping potential or stopping voltage is the minimum potential on the anode needed to stop all the electrons from reaching it. So recall this following equation. You remember this from an earlier video? Work is equal to change in kinetic energy equals Q delta V. So now we're going to apply the law of conservation of energy. Energy in equals energy out. And we're going to substitute this for the kinetic energy of the free electron. And Q delta V is going to be Q voltage stopping potential. Question 11. From the lab setup from question 9, you all need to memorize this lab setup. You're going to see it a lot. From the lab setup from question 9, draw a graph of the current versus potential difference across the anode and cathode with the same incoming frequencies and different intensities. So it says same incoming frequencies. If we both have the same incoming frequencies, the stopping potential is going to be the same. Okay? But the intensity, the current is going to be different. Because more intensity means more current. Write that down. More intensity means more currents. So in the graph, the incoming frequency of the incoming electromagnetic wave of the red line is the same as the green line. The intensity of the red line is greater than the intensity of the green line. So if F here is the same for both, then V sub S is going to be the same for both. So this unit or this topic, it's non-intuitive. It's not like classical mechanics. So you really got to visualize this and think about what's happening again and again. Question 12. From the lab setup from question 9, draw a graph of the current versus potential difference across the anode and cathode with different incoming frequencies. Okay? Different incoming frequencies. So if the incoming frequency is greater, then the stopping voltage will be greater. Because frequency is proportional to energy, right? E equals HF. The incoming frequency and the stopping voltage of the brown line is greater than that of the blue line. So if F is greater, then V sub S will also be greater. Question 13. What is the meaning of energy is quantized? Energy is not continuous. Energy comes in small packets and is discrete. Question 14. For the photoelectric effect, draw a current versus frequency graph below the threshold frequency and above the threshold frequency with the constant intensity of the incoming photons. Okay. So you can see if you're below the threshold frequency, there's no current. If you're above the threshold frequency, you're going to get a current. Question 15. For the photoelectric effect, draw two graphs. Current versus intensity graph below the threshold frequency and current versus intensity graph above the threshold frequency. So on the left side, current versus intensity if you're below the threshold frequency. You're not going to get a current. No electrons will leave the metal. If we're above the threshold frequency and we continue to increase the intensity, the current will increase. If the incoming photons have an energy which is at or above the threshold frequency, then there will be electrons ejected from the metal. The greater the intensity, the greater the current. Question 16. What is the energy content in joules of a light wave which has a wavelength of 4.40 times 10 to the 3 angstroms? So this is what we do. This says 4.4 to the 3. This says 4.4 to the minus 7. So I'll have to change that a bit. Question 17. What will be the energy content in joules of a light wave which has a frequency of 5.25 times 10 to the 14 hertz? Okay. So we're going to use the equation E equals HF. Question 18. A light wave has an energy content of 2.93 times 10 to the minus 19 joules. What will be the wavelength and frequency of this wave? So we were given energy and we could calculate the frequency using E equals HF. And we could calculate the wavelength also using E equals HF. Just substituting for F to be V over lambda. Question 19. A photoelectric experiment is performed and data is collected as shown below. Okay, so we have the wavelength here of the incoming photons, and we have the stopping potential of the electrons. Okay. Part A, determine the kinetic energies of the emitted photoelectrons in joules. So let's take a look at this equation. Q is a charge of an electron. So here are our answers here. Part B, determine the frequencies of the incoming light waves. V equals lambda F. F equals V over lambda. So we could use this equation here. So we could find the wavelength and the frequency of the incoming light waves. Part C, plot a graph comparing the energies of the emitted photoelectrons to the frequency of the incoming photons. So I use Microsoft Excel for this. You could see I have frequency and kinetic energy maximum. Part D, from your graph, calculate an experimental value for Planck's constant. So the best fit line told me the slope, which is 0.5371 times 10 to the minus 33 joules second. Okay, which is 5.37 times 10 to the minus 34 joules second, which is really close to 6.64 times 10 to the minus 34 joules second. Part E. From your graph, determine the cutoff frequency for this surface and the resulting work function for this surface. So we need to find the x-intercept to determine the cutoff frequency. This is when kinetic energy max is 0 joules. So you could see what I did. I'm just going to let E max, kinetic energy max, be 0 joules. And solve for F. And we need to find the y-intercept to determine the work function. So, part F, determine the equation describing the kinetic energies of the emitted photoelectrons as a function of the incoming light photons and the work function psi for the surface. So we have the equation of a line y equals mx plus b. And the horizontal is F, x is F, and the vertical is kinetic energy max. Y is kinetic energy max. Question 20. Light which has a wavelength of 890 angstroms is incident on a photoelectric surface which has a work function of minus 13.6 electron volts. Part A, what is the energy content in joules of this incoming light wave? We'll use V equals lambda F and E equals HF. Part B, how much energy in joules would be required to free the least strongly bound electron from the surface? Okay. So E equals HF. I apologize, this is not E equals HF. We were given 13.6 electron volts. Okay, so we're just going to convert electron volts to joules. Part C, what would be the kinetic energy of the emitted photoelectrons? Well, we're going to use this equation again. Okay. Part D, what will be the velocity of the emitted photoelectrons? We know kinetic energy max is 1/2 mv squared. And this is the mass of an electron. Question 21. Light, which has a wavelength of 3.7 times 10 to the 3 angstroms, is used to illuminate a photoelectric surface. As a result of this illumination, photoelectrons are emitted from the surface. A stopping potential of 1.25 volts is required to reduce the photocurrent to 0. Part A, what is the maximum kinetic energy of the emitted photoelectrons? Okay. Remember, W equals Q delta V. And we know Q, the charge of an electron, and delta V, we were given it, stopping potential of 1.25 volts. Part B, what is the energy content of the incoming photons? Well, this says in the problem 3.7 times 10 to the 3. This says 3.7 times 10 to the minus 7. So it was just converted from angstroms to meters. So E equals HF, and we know V equals lambda F. Part C, what is the work function of the surface in electron volts? So we're going to solve for psi.